Good, good afternoon, everyone. Can you guys see my slide?
Yes, yes.
So I'll be continuing on steam reforming process part. For this process, a catalyst is still required to accelerate the reaction, even though steam reforming is carried out at high temperature, which is above 1000 K, due to the very high stability of methane. The catalyst is contained tubes in tubes placed inside a furnace heated by combustion fuel. In this figure, it shows the steam reformer, which consists of two sections, which is convection section and radiation section. In this convection section, the heat recovered from hot flue gas is used for preheating of the gas feed and process steam and superheated steam generation, while for this radiant section of reforming reaction take place. In the radiant section, forming section take place, and after the sulfur removal, the natural gas feed is mixed with steam and optionally carbon dioxide and preheated to approximately 780 K before entering the reformer tubes. And the heat for the endothermic reforming reaction is supplied by combustion fuel in the reformer furnace, which carry out allothermal operation. Allothermal operation is heating from an external source, and this in gas will composition during the reformer may be further modified in additional process steps such as secondary reforming and or shift reactors that reduce their carbon monoxide content. So this figure shows a general arrangement of a typical steam reformer. The preheated process stream enters the catalyst tube through manifolds and pigtails, then flow downwards, which uh, located here, and the catalyst will flow downwards, and the product gas is collected in an outlet manifold, then pass upwards to the effluent chamber to be further processed. The outward the manifold here is located here. The tubes are carefully charged with catalyst particles evenly distributed over the tubes, and the catalyst bed should be dust-free. A furnace may contain 500 to 600 tubes with a length of 7 to 12 meter and inside diameter of between 70 and 130 millimeter. So reformer penthouse structure containing distribution system here is for feed, fuel and combustion air, including support system and operator access to burners and catalyst tube. It's located reformer radiant box with the catalyst tube arranged in multiple rows. Process gas boiler for cooling reformer effluent in single step approximately 620 Kelvin. Expressed here with associated steam drum in piggyback arrangement. And here is where combustion air preheated to reduce fuel consumption. Here is steam drum, which is to provide boiler water to boilers in the convection section. Here is convection section for heat recovery from flue gas leaving the radiant section, with preheat coils for the process and coils for steam generation or superheating of an air preheat. Combustion takes place here. Combustion air fan with air intake, and here is a stack for discharge of flue gases to safe location. So carbon formation in this steam reformer must be prevented for two main reasons. Firstly, coke deposition on the active side of the catalyst leads to deactivation. Second is carbon deposit grows so large, causing total blockage of the reformer tubes, resulting in hotspot, where formation of a layer of coke will cover the inner wall of the tubes of reformer. So hence the reformer condition must be chosen to limit the carbon formation. And this carbon forming reaction can be suppressed by adding excess steam. A common practice to operate the reformer at steam to carbon ratios of 2.5 to 4.5 mol steam per mol carbon, and the higher limit applying to higher hydrocarbons such as naphtha. And compared to methane, higher hydrocarbons exhibit a greater tendency to form carbonaceous deposits because they have larger carbon number. At higher temperature, which is above 920 K, steam cracking occurs to form alkenes that easily form carbon through this reaction. An additional advantage of using excess steam is that it enhances hydrocarbon conversion due to the lower partial pressure of hydrocarbons. Moving on to methane slip, um, most applications require syngas at elevated pressure. For example, in methanol synthesis, require pressure of 50 to 100 bar, and ammonia synthesis at even higher pressure. Thus, modern steam reformers operate at pressures far above atmospheric, although thermodynamically unfavorable, which is a direction in which energy state of product is higher than reactants. Advantages of operating at elevated pressure is a lower syngas compression cost and a smaller reformer size. But the downside is a lower methane conversion. To counterbalance the negative effect on the equilibrium, higher temperature are applied and excess steam is used. So this figure shows the effect of pressure and excess steam on the methane slip, which is percentage of unreacted methane. It is economically advantageous to operate at the highest possible pressure and consequently at the highest possible temperature. Tube material, however, places constraint on the temperatures and pressure that can be applied. A maximum limit exists for the operating temperature at a given pressure because of the creep limit of the reformer tubes. At typical reformer temperatures and pressure, an appreciable amount of methane is still present in the syngas produced. A low methane slip is often crucial for the economics of the process. There is a trend towards higher operating temperature exceeding 1200 Kelvin, which is made possible by the increasing strength of the tube materials. So here is the effect of the pressure. As you can see, higher temperature with higher pressure uh, will produce more methane slip. And here is the excess steam, which is high temperature and but lower ratio steam to methane will produce a higher methane slip. So advance in steam reforming. Improvement include better materials for reformer tubes, better control of carbon limits, better catalyst regarding sulfur tolerance and carbon deposition, and better process concept with high feedstock flexibility. So various modification of the basic steam reforming process in the previous figure that I showed implemented. And if natural gas feed is rich in higher hydrocarbons, or if naphtha is used as the feedstock, a preformer may be installed upstream the reformer furnace to convert this compound. This preformer is to react the hydrocarbon feed with steam to give a methane-rich product, which is suitable for further downstream. Hence, the worst carbon precursor are removed in advance, which allows operation of the actual reformer at lower steam to carbon ratio. And several different process configuration for reforming of higher hydrocarbons, including circulating fluidized bed membrane reformers, have been reported. And in these syngas plants, normally it will produce high pressure steam, which will be used only partly in this plant. So the heat exchange between high temperature of the reformer effluent with additional feed allowing a reformer part of the feed in a multi-tubular reactor without using a furnace. As for newly built syngas plant, this concept is usually not applied due to the severe corrosion, metal dusting inside the reactor, which requiring the selection of expensive materials. However, for capacity revamps, this concept is attractive, enabling typically 25% capacity increase at low investment cost. And that's all from module 3. So any question?
Question for Afifa. Let me ask first, then other students later you can ask also. I mean, you ask to the audience lah. Ask to me, ask towards me, or ask towards Afifa. Okay. So my question for Afifa, the reformer. What do you think that which type of reactor it is?
What type of reactor?
You remember your chemical reaction engineering? You got learn 4 types of reactor.
Yeah.
So this reactor inside this module, which type of reactor it is? Batch reactor, PSTR, PFR, PBR. Is it a batch reactor?
I think yes, maybe.
It is a batch reactor. How come?
Wait.
No, it's not a batch reactor. Is it a CSTR?
I think CST. No.
CSTR means continuous stirring kan?
Yeah.
Got stirring tak?
No. CSTR.
CSTR. Why?
Because continuous the speed will be continuous speed inside.
It is continuous, but other reactor, other than batch reactor, they are all continuous.
Continuous production.
Do you think it is a PFR because it looks like a tube? Cylindrical reactor? Do you remember what is a reactor? Okay, never mind. I guess you are confused or you are nervous or what. But I give the answer. In my opinion, I think it can be recognized as PFR or PBR because it is using tube. You can see that in the diagram. You cannot see in the diagram actually. The diagram is the tube is embedded inside the picture, but it use a lot of certain tubes and multi tubes. So tube, okay, in our basic chemical reaction engineering, we can consider it is a plug flow reactor lah. But because we are using catalyst, so somehow we can consider it as a packed back reactor also. But it is a cylindrical top to bottom or bottom to top flow operation. So we can consider it PBR or PFR. Okay. So Afifa, so why got the carbon formation problem in this module? Where is the carbon coming from?
Carbon.
Why got carbon? You are using methane then?
Yes. So, because methane contain carbon.
But you are reforming it with oxygen kan? Why you have carbon?
Mm, is it from the is it
Okay,
from the
I
tubes?
remember in your slide got one way saying that from the tube. No, the tube is metal. There is one equation listed in your slide just now, right?
Uh, uh,
Go down. Equation
from alkene.
from what?
Alkene.
But this alkane, it comes from the higher hydrocarbon kan? You look at the first bullet, higher hydrocarbons. But methane will not produce alkane kan?
Yes.
So
The
why suddenly got carbon?
catalyst use.
Catalyst don't have carbon. Catalyst is transition metal. Okay, let's say now you have a car. You know that you combust the fuel, you will have carbon kan? The
Uh,
black color.
Carbon dioxide.
No, the carbon dioxide is not black color.
Uh, 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 uh.
I just want the keywords there. All right. Okay. When you are combusting hydrocarbon, you may have incomplete combustion kan?
Yes.
Complete combustion, you may produce carbon because the reaction, that this is side reaction or unwanted reaction will occur to form carbon. In the reforming also will have that kind of issue.
Hydrocarbon.
Yeah, reaction with hydrocarbon, it always got the side reaction that will form carbon. Or the carbon is from hydrocarbon lah, because methane is hydrocarbon, that's why you have carbon. But why you have carbon is because the reaction with hydrocarbon will have so many multiple reaction, so many unwanted reaction, so many side reaction. One of it will produce carbon. Like in your slide example is the higher hydrocarbon will produce alkenes. Alkenes will then produce carbon. Methane also will produce something else. Then that something will produce carbon also.
Okay.
That's why you have carbon formation. Okay. So your presentation got got two graphs together. Can you go to that slide?
Okay.
Okay. Now my question is, which line is the best to choose in the operation? Which line is the best and why?
I think the highest, the lowest here, this line. Yeah, because it produce less methane slip.
Okay. You are right. How about the graph and
On the right, also the same. We are using the ratio 5 will produce.
in the real industrial operation? Do you think they're using one bar on the left?
No, because
So they are using 30 bar.
yes,
Why?
because Uh, because it is economically advantageous to operate at highest possible pressure and highest possible temperature.
Why is it economical?
More profitable, can produce more yield.
Uh, that's the same meaning. Why? The previous slide, you go to your previous slide,
Yeah.
and I think another previous. Why they use
Lower
compression in the high pressure?
syngas compression costs and a smaller reformer size is used.
Wait,
Ah,
you operate at higher pressure, but then it says lower syngas compression block
costs.
cost. Yeah lah. I mean, you say you don't want to spend money in compress it, but you are using high pressure also. How can you reduce the compression cost? If you are doing one bar, then you don't need compression kan? That is zero syngas compression cost kan?
Yes.
Yes.
Ah,
Then you cannot agree with me, you know. I'm asking question here. Okay? You have to give me reason.
so
That is in the first bullet. Can you explain first bullet to me?
here,
The first one. The answer is there.
because uh, requires to produce syngas must use elevated pressure.
No, you
No.
are. This application they want the syngas at high pressure. Not to produce syngas, you need high pressure. No. To produce syngas, you need low pressure. Low pressure is better, but we still do at high pressure. Why? Because subsequently, the syngas that you produce, they will use that syngas to produce methanol, to produce ammonia. And when you use that to produce ammonia and methanol, they want the syngas in high pressure. So at the end, you still need high pressure syngas. Therefore, we rather in the beginning we already use high pressure because later on we don't need to compress again. That is why the bullet number 3 says that lower syngas compression cost. Do you get me?
Maybe.
No, you cannot understand. Okay, all right. So before we produce syngas, we know that thermodynamically, if you use low pressure, you can produce more syngas from methane. Okay. After you produce the syngas, that syngas you need to produce. You are use syngas. You are using syngas as feedstock for some other thing like methanol and ammonia. But in order to produce methanol from syngas, you want the syngas to be in high pressure. So, since the syngas you want to produce, later on you want to use is in high pressure, why not we produce the syngas in high pressure? Because we can compress once only. And we compress earlier is better than we compress later somehow. Okay. And after, if you compress earlier, you need a smaller reformer size. Smaller reformer size means lower cost for that reformer. Because in industry, the reactor size will be translated into the cost lah. Bigger, more expensive. Smaller, less expensive.
Okay.
That is the whole reason here why the chemistry told us that we should run at low pressure. But economy tells us to run at high pressure. Okay, as an engineer, we have a lot of this kind of sort of dilemma or situation to choose which one we want to use. So mostly we look at economy, we look at safety, we look at what else? Environment. Okay, here in chemistry, of course, we look at low pressure and why we want to use high pressure. But economy told us we use high pressure, we can earn more money. The reason is there lah. Okay, I also wish everyone can get the idea that this many of the texts here it mostly discuss which one is the most economical. Like we learn about the history of many processes. Why they afterwards they change. All is because more economical, more safe, more environmental friendly, and so on. Okay? I hope that you can catch the main idea, every one of you. Of this. So when you read the text, there is a lot of meaning at the back. So you need to understand why, okay, the engineer or the designer is choosing this over there. In your plant design, you are doing what? Process selection kan? This is sort